Welcome to The Explainer. Today, we're unpacking a topic that is absolutely fundamental to our future, yet honestly, it rarely gets the spotlight it deserves. We hear about artificial intelligence literally every single day, right? We hear about how smart it is, how incredibly capable it is, and of course, how safe it is. But here's the really fascinating part. How do we actually know? Today, we're going to explore the core theme of how we evaluate the safety and intelligence of AI. We're going to look at the mechanics of judgment itself, kind of pulling back the curtain on why testing AI isn't just about getting the right answer. It's about something much, much deeper.
Okay, let's dive into this. Before we even touch a line of code or look at a complex neural network, we need to ask ourselves this very relatable but incredibly broad question. Whether it's people, systems, or AI, how do we actually evaluate a subject? Think about it for a second. When you're judging a new colleague, picking a smartphone brand, or looking at an artificial intelligence, you can't possibly observe them in every single situation they'll ever encounter. That is literally impossible. So we have to rely on a specific mental framework to actually make those judgments. Which brings us to our first section, the essence of evaluation, and how we go about making generalizations from our observations. So, because we can never observe a subject in every possible scenario, we essentially have to stretch a tiny sliver of reality into a much broader understanding. And that mental stretching, it actually has a formal name. It's called inductive reasoning. It's the process of finding repeating characteristics from observed situations to determine a subject's general traits. Basically, we look at a few specific instances, we hunt for repeating patterns, and we say, okay, this subject generally behaves this way. Whether you're judging a company's customer service, a person's reliability, or an AI's ability to summarize a massive document, you are inherently using inductive reasoning. Let's ground this in a quick, everyday analogy. We don't judge human character based on just one single answer, do we? If you ask a friend a question, their one response doesn't suddenly define their entire personality. Instead, you ask them multiple questions over time, and you're looking for converging patterns. If their answers wildly fluctuate, say they're overly generous one day and incredibly selfish the next, in the exact same scenario, well, it becomes impossible to pinpoint their true nature. You simply can't generalize them. And you know what? The exact same logic applies to evaluating anything else, including complex neural networks. Let's move to and see how this builds. Here is the step-by-step anatomy of judgment. It all starts with an observation. From there, we look for a repeating pattern. And when we find it, those results undergo convergence, which then allows us to make a generalization, finally leading to a solid conclusion. Now, a really important note here. Convergence doesn't mean the results are perfectly identical every single time. It just means they fall within a consistent, expected range. Basically, there's a common pattern that we can rely on. Moving into section 2, we're looking at consistency, building reliability, which really is the foundation of trust. We just built this beautiful chain of logic. But what happens if the middle of that chain, the convergence, that repeating pattern, is completely broken? Well, the whole thing falls apart. And this brings us to a crucial distinction. Consistency does not guarantee absolute truth. Just because someone consistently gives you the same answer doesn't magically make it a universal fact. I mean, they could just be consistently wrong. But here's the flip side. Without consistency, generalization becomes entirely impossible. If the results are constantly shifting around, you completely lose the ability to trust any generalized conclusion you try to draw. So how do we actually secure this consistency, particularly when we're dealing with advanced tech systems? Well, we look for 3 main pillars. First up is repeatability. Do you get similar results under the exact same conditions? Like, if you ask an AI model the exact same prompt twice, does it give you a similar output? Second is reproducibility. If you completely recreate the testing environment, maybe with a different researcher or a slightly varied setup, do you still get similar results? And third, sustainability. Are these characteristics maintained as time passes, or when entirely new conditions are introduced? Say you update the underlying dataset or ask a completely novel prompt, does the model maintain its core safety constraints? Securing these 3 elements is exactly what allows us to confidently link individual, isolated observations into one reliable, trustworthy conclusion. Now for section 3, the true role of ground truth and anchoring the evaluation. This actually leads us to a fascinating pivot, because to know if something is consistent, you absolutely need a baseline. What exactly are we comparing these results against? Well, that is our ground truth. Now, what's really interesting here is the formal definition. Ground truth is a predefined, common reference used to fix evaluation criteria, allowing for comparative consistency. I want to emphasize something very strongly here. Ground truth is not about uncovering some profound, absolute reality of the universe. Not at all. It is simply a fixed anchor. Think of it like an answer key on a student's multiple choice test. The answer key just gives the teacher a fixed reference point to consistently grade every single student.
And this brilliantly illustrates the massive divide in how we train and evaluate AI today. On one side, you've got supervised learning. This relies on a fixed ground truth. Because there are clear labels, just like our answer key, it's incredibly easy to compare results, repeat evaluations, and verify that consistency. But on the other side, you have self-supervised or unsupervised learning. This type of AI discovers patterns in raw data all on its own. It lacks that explicit external reference, which, as you can imagine, makes verifying its consistency so much harder. Now, please make sure you catch this, because it's vital. The difference here is not about the AI's intelligence or its accuracy. We aren't up here judging which AI is smarter. We are looking strictly at the evaluation structure itself. A supervised model isn't necessarily better, it's just inherently easier for us humans to reliably test because we have those fixed reference points. With unsupervised models, verifying that the AI's newly discovered patterns will actually hold up when new data is introduced, well, that's a whole separate and very difficult challenge.
Which brings us to Section 4, the core question of AI safety, moving beyond just getting the right answer.
Let's take everything we just learned and apply it directly to the frontier of AI safety. We see statements like this in the news all the time from tech companies, right? This model is generally safe. But think about what we've discussed today. This statement is a massive, monumental leap of inductive generalization. They're taking a limited set of test observations and generalizing them to say the AI will be totally safe out in the wildly unpredictable real world. Making a claim this huge requires absolute, rock-solid consistency in our testing methods. And honestly, here is the absolute nightmare scenario for AI researchers. When they test an AI and the evaluation results fluctuate, what is the actual cause? Is the model itself acting dangerously? Or was there just a subtle change in the data distribution? Or even worse, did the evaluation criteria, the test itself, shift without us even realizing? If our testing framework isn't consistent, an unexpected failure might mean the AI is turning harmful, or it might just mean our test is fundamentally flawed. And the scary part? We wouldn't be able to tell the difference. So the crucial point is this. The fundamental problem in AI safety isn't just AI performance. It is the reliability of our evaluation methods. Finding out if the AI gave the right answer is really only half the battle. Evaluation reliability is its own massive independent research field, and it is absolutely crucial to ensuring a safe future with this technology. We literally have to figure out how to evaluate the evaluators. I want to leave you with this final, provocative thought drawn straight from the core of this issue. The next time you read a headline claiming an AI has passed some major milestone or been deemed completely safe, don't just ask how well it did. You need to ask, how consistently can we repeat and reproduce the evaluation that judge the AI as doing well? Because if we can't trust the test, we simply can't trust the results. Thank you so much for joining me in this explainer. Keep asking the hard questions, and I'll catch you in the next one.